Ancient Babylon's engineering secrets have been hiding in plain sight for thousands of years. This civilization, flourishing between the Tigris and Euphrates rivers, gifted humanity with marvels that built the very foundation of our modern world. By the end of this exploration, you will know the 28 hidden innovations that reshaped the ancient world and still influence your life today. How did they construct massive arches without modern tools? And what mathematical mystery did they grasp centuries before anyone else? What does it truly mean to build a legacy that outlasts empires? Between two mighty rivers, a civilization was forged by necessity. The Tigris and Euphrates did not simply provide water, they presented a constant life or death challenge. Annual floods could be devastating, while summer droughts threatened famine. To survive here, the Babylonians had to become masters of their environment, and this relentless demand for solutions became the engine of their engineering genius. Their society was built not just on mud bricks, but on a profound respect for knowledge. Scribes trained for years in specialized schools, meticulously recording everything from astronomical observations to complex mathematical formulas on clay tablets. These were not dusty archives, but active toolkits for administrators and builders. Imagine the value of a culture where a mathematician's calculation for a canal slope was considered as vital as a soldier's strength. This deep-seated cultural commitment to learning transformed practical problems into opportunities for invention. It was within this unique context that their greatest innovations took root, each one a direct answer to a question posed by the harsh, beautiful landscape they called home. Understanding this foundation is like being handed the key to a locked door, behind which lie 28 secrets that would change the world. Their first great innovation rose not from stone, but from the very earth beneath their feet. The Babylonian Arch was a quiet revolution in structural logic. Before this, most grand structures relied on the post and lintel system, a simple but limited method where a horizontal beam rests on two vertical posts. This approach could only span short distances, and the weight pressing down created immense stress on the central beam. The Babylonians saw a different path, a curved one. They discovered that by arranging specially shaped bricks into a semicircle, they could redirect the force of gravity. Instead of pushing straight down, the weight was transformed, channeled outward and down along the curve of the arch to the supporting walls on either side. This distribution of force was a game changer. It meant that the structure actually became stronger under load, the compression locking the bricks more tightly together. Think of it not as a burden to be borne, but as a flow of energy to be guided. This principle allowed them to create soaring city gates that felt both immense and inviting, and to build sturdy, waterproof vaults for underground storage and tunnels. The magnificent Ishtar Gate, with its dazzling blue glazed bricks and detailed animal reliefs, was not just a wall, it was a monumental demonstration of this very idea. Its grandeur was made possible by the hidden strength of the arch. This fundamental concept would travel through the centuries, adopted and refined by later empires like the Romans, who would use it to build aqueducts and colossal buildings. But its origin lies here, in the mud brick and brilliant minds of Babylon, a hidden cornerstone of our built world that we still walk under every single day. That same genius for channeling immense forces also had to be contained within the very building blocks themselves. The Babylonians confronted a landscape with little stone, but they possessed an endless supply of raw material, the very soil under their feet. Yet ordinary mud crumbles, it washes away with the first rain. Their monumental ambition demanded something far more resilient, and so they engineered the humble brick into a technological marvel. This was not mere mud slapped into a mold. It was a science of mixture and process. They became master chemists of the earth, experimenting with different clay compositions. They discovered that by adding chopped straw, they created a fibrous network within the brick, a hidden reinforcement that drastically reduced cracking as the material dried and expanded. For even greater endurance, especially against their greatest enemy, water, they sometimes mixed in bitumen, a natural tar that seeped from the ground. This ancient waterproofing agent created bricks that could withstand the elements for centuries. The process itself was a feat of standardization. These specially formulated clay mixtures were pressed into wooden molds to create bricks of a consistent size and shape. Some were left to bake under the fierce Mesopotamian sun, while others were fired in kilns, a process that transformed soft clay into a hard, ceramic-like stone. This standardization was their secret to speed and scale. Think of it as an ancient assembly line. With every brick identical, teams of workers could build at an incredible pace, laying course after perfect course. It was this innovation that made the impossible possible. The great ziggurat of Babylon, a towering mountain of a building meant to bridge the earth and the heavens, was constructed from millions of these engineered bricks. The city's formidable walls, wide enough for chariots to ride atop, rose from this same foundation. This technology was so effective it became a cultural export, spreading throughout the region and influencing empires that followed. The very substance of their cities, a perfected blend of mud and mind, became one of the most enduring legacies of the ancient world. But that mastery of materials and structures needed a grand design to bring it all together. The true brilliance of Babylon extended beyond individual buildings into the very blueprint of the city itself. These were not chaotic settlements that simply grew over time. They were meticulously planned urban centers, engineered for efficiency, control, and a surprisingly modern quality of life. At the heart of this was the grid layout. Unlike the winding, narrow alleys common in many ancient towns, Babylonian cities were organized with straight, broad avenues that intersected at right angles. This was a revolutionary concept. These orderly streets did more than just look impressive. They facilitated the smooth flow of people and goods, turning the city into a dynamic hub for trade. They allowed for easy military movement and, crucially, made the entire city manageable for administrators. Imagine trying to govern a tangled maze versus a clearly mapped grid. This systematic design extended to zoning. Specific districts were designated for residential homes, bustling commercial markets, and sacred religious complexes. This separation ensured that the noise and activity of a merchant's stall did not intrude upon the space meant for worship or family life. It was an early recognition that a city is a complex organism, and its parts must work in harmony. The great city of Babylon itself was a living testament to this principle, a sprawling metropolis that functioned with an order that would impress a modern urban planner. This foundational idea of the planned city did not vanish with the empire. It traveled west, influencing Greek city planners who are often credited with the concept, and echoes of this Babylonian logic can be found in the street grids of cities across the world today. It is a hidden innovation you likely experience whenever you navigate your own town, a 4,000-year-old solution to the eternal challenge of living together. That grand design of streets and buildings would have been meaningless without the lifeblood that sustained it, water. In a land where the sun was relentless and rainfall unpredictable, the Babylonians turned their engineering genius to the rivers themselves, creating a hidden web of canals and channels that transformed the desert into a garden. This was not just simple digging. It was a symphony of hydrology, a complex system designed to tame the twin threats of flood and drought. They constructed massive main canals, arteries that branched into smaller channels, and finally into the delicate capillaries of irrigation ditches that fed each and every field. To control this flowing network, they engineered brilliant devices. Sluice gates acted as adjustable valves made from wood or stone that could be raised or lowered to precisely regulate how much water entered a secondary canal. Weirs, which are low dams built across a waterway, allowed them to pool water and maintain a consistent depth, ensuring a steady, reliable flow even during drier periods. The precision required was staggering. Surveyors used levels and sighting instruments to ensure canals had the exact gentle slope needed. Too steep, and the water would rush through, eroding the channels. Too flat, and the water would stagnate, choking the system with silt. This constant, careful maintenance was a civic duty, a shared responsibility that kept the entire civilization alive. By mastering this flow, they achieved the impossible. They turned the volatile Tigris and Euphrates into a predictable agricultural engine. Vast fields of barley, dates, and wheat flourished where little grew before. This abundance did more than just fill stomachs. It created surplus, the fundamental ingredient for cities, for trade, for specialization, and for art. The bustling markets of Babylon, its schools of scribes, and its towering ziggurats all stood upon a foundation of engineered water. This hidden network beneath the soil was the true source of their power, a quiet innovation that turned a challenging environment into the cradle of civilization. But that life-giving water was only half the agricultural equation. The Babylonian farmer faced a monumental task, preparing the hard earth and then carefully sowing each precious seed by hand. This slow, back-breaking process limited how much food could be grown, directly capping the size of their cities. Then came an invention so elegantly simple it changed everything: the cedar plow. This was no ordinary plow. It was a masterstroke of practical engineering, a single device that combined two separate, labor-intensive jobs. As the oxen pulled it forward, a sharp metal point called a plowshare would cut a neat furrow into the sun-baked soil. But here is the brilliant part. Attached to the plow was a funnel, a kind of tube that led down to the freshly opened earth. A farmer would walk behind, pouring seeds into this funnel. The seeds would slide down the tube and drop directly into the furrow, and a following piece of the device would then gently sweep soil over them, covering the seeds perfectly. In one smooth, continuous motion, the ground was tilled, the seeds were planted at a consistent depth, and they were covered for protection. This was the ancient world's first fully integrated farming machine. Think of the efficiency. What once required two separate teams of laborers and twice the time was now a single operation. The savings in human effort were enormous. But the benefits went even deeper. Because the seeds were planted in neat, straight rows at a uniform depth, they germinated more reliably and grew stronger. Weeds between the rows were easier to spot and remove. This systematic approach meant that every single seed had the best possible chance to thrive. The result was a dramatic surge in crop yields. Fields that once produced just enough to feed a village could now generate a surplus large enough to sustain a bustling city. This tool did not just make farming easier. It broke the ancient ceiling on food production. The abundance it created fed the scribes, the artisans, the soldiers, and the engineers who were busy building the rest of this civilization. A hidden innovation, born from the mind of a practical farmer, became the quiet engine that powered an empire's growth. With their fields flourishing and their cities expanding, the Babylonians faced a new challenge of scale. How could their rulers and merchants comprehend the vastness of their own empire, a sprawling network of cities, canals, and trade routes stretching across the landscape? The answer was etched not on paper but into the damp, pliable surface of clay. They created the world's first known maps. The most famous of these, the Babylonian world map, is a stunning artifact. It depicts the Earth as a flat, circular disk, with Babylon itself sitting proudly at the very center. Radiating out from it are other known cities, all surrounded by a bitter river, and beyond that, the uncharted territories marked simply as strange and distant land. This was not just a picture, it was a conceptual tool, an attempt to make sense of the entire known world and their place within it. But these maps went far beyond philosophical wonder. They were intensely practical instruments of power and commerce. Administrators used detailed city plans to manage land ownership and settle boundary disputes. A clay tablet could show the exact layout of a district, the location of a temple, or the course of an irrigation canal, turning complex spatial relationships into something a scribe could hold in his hand. For merchants, route maps were invaluable. They charted the paths between major cities, noting distances, mountain passes, and sources of fresh water. This was the ancient equivalent of a modern logistics network, allowing goods to flow reliably across hundreds of miles. The symbols they developed became a universal language. A triangle might represent a mountain, a wavy line a river, and a small rectangle a building or a town. This system of standardized symbols meant that anyone trained to read a map, from a tax collector to a caravan master, could understand the information it contained. This was the true birth of cartography, the science of mapping. It transformed the abstract idea of space into a manageable, communicable plan. The ability to see your world from above, to hold its representation and make decisions based on that knowledge, was a profound shift in human consciousness. This hidden innovation did not just guide travelers, it laid the foundational stones for all future exploration, allowing humanity to first chart and then truly comprehend the world around them. That meticulous mapping of space demanded an equally precise measurement of time. The Babylonians engineered a device that gave the day its first formal structure, the sundial. This was not a simple garden ornament. It was a carefully calculated instrument, a marriage of astronomy and practical engineering. At its heart was the gnomon, a vertical rod or blade that cast a definitive shadow onto a flat, marked surface. As the sun journeyed across the sky, that shadow would sweep along the dial, tracing a path that divided the daylight into measurable segments, but the genius lay in the calibration. The Babylonians knew the sun's path was not constant. It changed with the seasons. A sundial that worked perfectly in the height of summer would be grossly inaccurate in the depths of winter. So they used their profound knowledge of the stars and the solar year to create dials with curved, complex hour lines. These lines accounted for the sun's shifting altitude, ensuring that an hour was an hour, regardless of the month. This was a hidden layer of mathematical sophistication, a direct application of their celestial observations to the needs of the Earth. The impact of this temporal organization rippled through every aspect of their society. A farmer could now schedule irrigation for the coolest parts of the day with newfound precision. Priests could announce the exact moment for a sacred ritual. Administrators could coordinate the work of thousands of laborers, all synchronized by the moving shadow on a stone disk. Time was no longer just the vague passage from dawn to dusk. It became a resource that could be managed, allocated, and made efficient. This was the quiet beginning of the scheduled day, a concept so fundamental to our modern lives that we rarely pause to consider its origin. The sundial was a silent revolution, turning the infinite flow of moments into a tangible, engineered system. and placing the rhythm of human activity in perfect harmony with the cosmos. That mastery of time and space was built upon a substance pulled straight from the earth, a sticky, black secret that made their world watertight. Bitumen was the miracle material of the ancient Near East, a natural tar that seeped to the surface in oil seeps, and the Babylonians became its ultimate alchemists. They recognized its incredible properties, its stubborn resistance to water, and they deployed it with brilliant practicality across their civilization. For a society living between two powerful rivers, waterproofing was not a luxury, it was a necessity for survival. They smeared this thick, viscous pitch onto the hulls of their trading boats, creating a flexible, impermeable seal that kept the river from swamping their precious cargo. They coated the insides of woven reed baskets, turning fragile containers into sturdy vessels that could hold water or grain without leaking a single drop. Even the foundations of their greatest buildings were protected by layers of bitumen, a hidden barrier against ground moisture that prevented their monumental walls from sinking or crumbling from below. But its use went far beyond a simple sealant. They mixed bitumen with sand and crushed limestone to create a powerful, durable mortar. This black cement held the bricks of their city walls together, adding a resilience that plain mud could never achieve. It was a glue that could last for centuries. This was innovation born from pure necessity, a perfect example of looking at the resources right under your feet and asking, what can this do? They did not invent bitumen, but they engineered its application on a grand scale, transforming a sticky, natural nuisance into the hidden shield that preserved their ships, their goods, and their very buildings from the relentless challenge of water. The strength of their plows and the precision of their maps were forged in fire. Babylonian metalworkers were not just artisans, they were early materials scientists, unlocking the secrets hidden within raw ore. Their mastery began with bronze, an alloy created by smelting copper and tin together. This was no simple melting. It was a delicate chemical dance performed in clay furnaces, a process requiring precise control of temperature and airflow to extract the pure metals and combine them into a substance far stronger than either component alone. This bronze was then poured into molds, but for objects of true complexity, they employed a technique of breathtaking ingenuity, the lost wax method. A sculptor would first create a perfect model of the desired object, perhaps a ceremonial weapon or a god statue, using beeswax. This wax model was then encased in a thick layer of clay, forming a mold. When the mold was fired in a kiln, the wax inside would melt and drain out through a small hole, leaving behind a perfect, hollow cavity. Molten bronze was then poured into this empty space. Once the metal cooled and hardened, the clay mold was broken away, revealing a metal object that captured every fine detail of the original wax sculpture. This process allowed for a level of artistry and complexity that simple carving could never achieve. But the true impact of this metallurgical genius was felt not in temples, but in fields and on battlefields. The same knowledge that produced intricate art was channeled into creating hardened bronze and later iron plowshares. These stronger, sharper tips could cut deeper into the tough soil, turning it more effectively and making the cedar plow even more efficient. For the military, it meant weapons that held a keener edge and armor that could better deflect a blow. This hidden art provided the material backbone for the entire civilization. The durable tools that built the canals, the strong weapons that defended the walls, and the sharp plows that fed the people all sprang from this fiery innovation. Their metallurgical secrets, carried along trade routes and through conquest, became a foundational technology, fueling progress across the ancient world and giving every subsequent empire a stronger foundation upon which to build. That mastery of fire and metal gave them the strength to shape the world, but another innovation gave that world its momentum. The Babylonians took the fundamental concept of the wheel and engineered it into a tool of pure efficiency. While the wheel itself was an older invention, it was in their hands that it found its true dual purpose, transforming both the artist's studio and the battlefield with equal force. In the workshop, the potter's wheel became a quiet revolution. Before its widespread use, every pot, bowl, and storage jar was painstakingly coiled and shaped by hand, a slow and inconsistent process. The introduction of the fast, rotating wheel changed everything. A lump of clay could be centered on the spinning disc and with skilled hands be coaxed into a perfectly symmetrical vessel in a fraction of the time. This was the ancient world's first encounter with true mass production. Workshops could now output hundreds of identical containers, each one strong, uniform, and perfectly functional. Think of the impact. Standardized jars meant predictable volumes for trading grain and oil. Sturdy, mass-produced pots became the essential storage units for every household and granary. This ceramic efficiency fueled the entire economy, from the merchant's ledger to the family's dinner table. But the wheel's power did not stop at the workshop door. Their engineers took the same principle and scaled it up, crafting robust wheels for chariots. These were not simple solid discs. They were sophisticated assemblies, often with a wooden frame, a leather tire soaked in water to shrink it tight, and sometimes even a metal rim for added durability. The development of spoked wheels was a particular breakthrough, making the chariots significantly lighter and faster without sacrificing strength. This new mobility transformed their military. Chariots became the swift, terrifying shock troops of the ancient world, allowing for rapid maneuvers, flanking attacks, and a mobile platform for archers. A Babylonian general could now control the battlefield from a distance, his forces moving with a speed that foot soldiers could not hope to match. The same rotational force that spun a potter's clay also propelled their armies to victory. This dual application of the wheel for both creation and conquest reveals the full scope of their engineering mindset. They saw a simple principle and asked not just what it could do, but how it could be perfected to serve every facet of their civilization. The humble wheel, refined in their hands, became an engine of both commerce and power, accelerating the pace of ancient life in ways that still echo today. Their chariots and potter's wheels spun on a foundation of pure numbers, but those numbers held a secret. Babylonian mathematicians grappled with an invisible problem, the empty space in their calculations. Their solution was a quiet conceptual leap, an early precursor to the idea of zero. Working within their sophisticated base 60 system, they needed a way to distinguish between numbers like 61 and 361. Writing them down without some kind of marker was confusing, so they began using a simple placeholder, initially just a blank space between their wedge-shaped cuneiform numerals. Later, they refined this into a specific symbol, two small angled wedges, to mark a position where no number existed. This was not yet zero as a number itself, a concept of nothingness, but it was the crucial first step. It was a symbol for absence, a punctuation mark in the language of mathematics that gave all the other numbers their proper place and value. This innovation in positional notation was revolutionary. It meant that a single symbol, like a wedge for one, could represent 1 or 60 or 3600, depending on its position relative to that empty space. Suddenly, writing and calculating with very large numbers became dramatically more efficient. This new power had immediate, practical consequences. Astronomers could chart the paths of planets with greater accuracy over long cycles. Engineers could compute the volumes of immense construction projects or the precise angles for a canal slope. a land surveyor could now clearly document a field's dimensions without ambiguity, ensuring fair ownership and taxation. This was a hidden pillar supporting their entire engineered world. The concept itself was a seed. It traveled the ancient trade routes, likely influencing Indian mathematicians who would centuries later transform this placeholder into the number 0, a profound philosophical and mathematical concept in its own right. From there, it passed into the Arabic numerical system and eventually to the world. Every time you see a number like 1005, that 0 holding the tens and hundreds place, you are witnessing the faint 4,000-year-old echo of a Babylonian scribe making a mark to show that there was nothing there at all. Their mathematical genius extended far beyond the abstract, touching the very ground they walked on. Centuries before the Greek philosopher Pythagoras was born, Babylonian surveyors were already applying the principle that bears his name. A famous clay tablet known as Plimpton 322 is not just a list of numbers, it is a sophisticated trigonometric table, a working tool that clearly demonstrates their understanding of the relationship between the sides of a right triangle. They knew that for a triangle with a perfect right angle, the area of the square on the long side was always equal to the combined areas of the squares on the two shorter sides. This was not a theoretical proof for them, but a practical fact, an empirical rule discovered through generations of building and measuring. Imagine a team of engineers planning a new canal. They needed it to run perfectly straight for miles. To ensure this, they would set up a series of right angles along the proposed route. Using a long, knotted rope, they could quickly form a triangle with sides measuring 3, 4, and 5 units. They knew that if the rope was stretched into this specific ratio, the angle between the 3 and 4 unit sides would be perfectly square. This simple, brilliant trick allowed them to lay out precise 90-degree angles across vast distances, guaranteeing their canals did not waver. The same principle was vital for construction. Before laying the foundation for a temple or a ziggurat, surveyors used this geometric knowledge to check that the corners were true right angles, ensuring the entire structure would rise straight and stable. It was the hidden geometry behind their architectural perfection. While they may not have written a formal theorem, their clay tablets reveal a deep, working knowledge of these triangular relationships, a tool honed by necessity and applied on a colossal scale. This practical geometry was the silent partner to every grand structure and every miles-long canal, a hidden innovation that would much later be given a famous name, but which first truly lived and breathed in the dust and sun of ancient Babylon. This mathematical precision and responsibility for construction quality was not merely a professional guideline, it was the law of the land, the code of Hammurabi, etched onto a towering black stone stele for all to see, contained some of the world's first known engineering regulations. This was not just a list of crimes and punishments, it was a sophisticated legal framework designed to ensure public safety and trust in the built environment. Specific clauses addressed construction directly, holding builders to a remarkable standard of accountability. One famous law stated clearly that if a builder constructed a house for someone and that house collapsed, killing the owner, then the builder would be put to death. If the collapse killed the owner's son, then the builder's own son would be executed. The principle was stark and absolute. The consequences for failure were severe and personal. Think about the powerful incentive this created. A builder could not cut corners, could not use substandard materials, and could not rush the foundation. His own life and the life of his family literally depended on the structural integrity of his work. This legal pressure fostered a culture of meticulousness, from the mixing of mortar to the alignment of bricks. It promoted reliability in every project, from the simplest merchant's house to the most complex temple complex. People needed to believe that the walls around them would not crumble, that the roof over their head was secure. This code provided that assurance, transforming construction from a mere trade into a solemn, legally binding responsibility. It was a hidden innovation in governance, a brilliant fusion of law and engineering that forced excellence and created a more orderly and ultimately safer society for every citizen who walked its streets. This legal demand for structural perfection found its ultimate expression in the movement of water itself. The Babylonian Aqueduct was a masterpiece of gravitational engineering, a stone and brick artery that defied the very lay of the land. These were not the towering arcades of a later empire, but ingenious channels that snaked across the countryside, carrying life-giving water from distant springs and rivers to places it had never reached before. Their construction was a direct answer to a simple, brutal limitation. A city could only grow as large as its local water supply allowed. Wells could only be dug so deep, and relying solely on the erratic rivers kept populations huddled along their banks. To break this geographic leash, their engineers designed channels that maintained a constant, gentle downhill slope from source to destination. This required an astonishingly precise understanding of hydraulics and elevation. Surveyors would map the terrain for miles, calculating the subtlest of grades to ensure water would flow steadily and smoothly, without rushing so fast it eroded the channel or moving so slow it stagnated with silt. They built these channels from their most durable materials, fired bricks sealed with bitumen mortar to prevent leaks, and often supported them on robust arches when they needed to cross a valley or maintain their crucial elevation across flat plains. Imagine the impact on a remote farming settlement. For generations they depended on unpredictable rain. Then, one day, a steady stream of fresh water begins flowing through a man-made river right to their fields. Crop yields would skyrocket, new land could be cultivated. For a city, it meant public fountains and cleaner water, improving health and allowing neighborhoods to expand away from the river's edge. This was more than just plumbing, it was a tool of territorial control and urban liberation. While the Romans would later perfect the form into monumental architecture, the fundamental principle of the long-distance, gravity-fed aqueduct was actively at work here in the heart of the ancient Near East. It was a hidden current of progress, a deliberate reshaping of the landscape to serve human ambition, one steady drip of water at a time. That same need for control over the flow of water found a parallel in the protection of possessions. In a society growing rich with trade and complex with administration, the simple bar across a door was no longer enough. Babylonian craftsmen responded with an invention that would become a universal symbol of security, the lock and key. Theirs were not the small, metal devices we know today, but often large, intricate mechanisms carved from wood and reinforced with bronze. The core of their design was a stroke of genius, a principle so effective it remains at the heart of most modern locks. Inside a wooden housing, a series of pins of varying lengths would fall into holes in a sliding bolt, effectively jamming it in place. The key was a uniquely shaped wooden or metal prod, often resembling a large, ornate toothbrush with pegs sticking out from its end. Only the correct key, with its pegs cut to the exact heights, could be inserted to push the internal pins up to a precise line. When all the pins were aligned perfectly, the bolt was free to slide, unlocking the door or chest. This was the birth of the pin tumbler lock. Think of the profound shift this represented. For the first time, security was not just about physical strength or a guard's vigilance. It was about knowledge, about a unique object that granted access. A merchant could now lock a warehouse filled with goods, secure in the knowledge that only he or a trusted lieutenant with the matching key could open it. A temple could safeguard its sacred relics and financial records. In the bustling administrative centers, where clay tablets held sensitive information on taxes and laws, these locks protected the very data that ran the empire. This innovation speaks volumes about their society. It reveals a deep concern for individual privacy and property rights, a necessary development for any complex urban civilization to function. The simple act of turning a key today is a direct legacy of that Babylonian desire to create a private, secure space within a crowded and interconnected world. Their ambitions did not stop at the city walls or the water channels. They reached for the sky itself. Babylonian architects mastered the art of vertical construction, engineering multi-story buildings that transformed the flat Mesopotamian horizon into a landscape of human achievement. The most spectacular of these were the ziggurats, colossal stepped pyramids that served as spiritual nerve centers for their cities. These were not merely large piles of brick. They were meticulously calculated structures, each tier slightly smaller than the one below, creating a stable, terraced form that could safely ascend to dizzying heights. This design required a deep, practical understanding of load bearing. The immense weight of each level had to be channeled perfectly down through the thick, tapering walls to a foundation dug deep into the earth, a foundation engineered to prevent the entire monument from sinking or tilting over centuries. Access was another feat. Broad, ceremonial staircases scaled the sides, their angles and supports carefully integrated into the main structure to maintain balance and provide a stable path for countless priests and processions. The legendary Etemenanke ziggurat in Babylon, said to have inspired the biblical Tower of Babel, was the ultimate expression of this vision. Its name meant the foundation of heaven and earth, a testament to its perceived role as a bridge between the human and the divine. Constructing such a giant was as much an organizational miracle as an architectural one. It demanded the coordinated labor of thousands of workers, from bakers feeding the crews to scribes tracking the distribution of millions of bricks. This ability to marshal and manage such a vast force for a single, non-military purpose reveals a hidden layer of their genius. The ziggurat's form, a man-made mountain pointing to the heavens, became a powerful cultural export, influencing the pyramids of Egypt and later structures across the ancient world. It stands as a hidden icon, a perfect fusion of religious devotion, raw engineering ambition, and the sheer logistical power needed to reshape the very skyline. That same precision in building and trade demanded a universal language of measurement. Without a shared standard, a merchant in one city could never trust the length of cloth sold in another, and an engineer could not send precise plans for a canal to a distant province. The Babylonian solution was to create and enforce a system of standardized units that held their empire together. The most fundamental of these was the cubit, a unit of length originally based on the distance from a man's elbow to the tip of his middle finger. But this was no rough estimate. The royal cubit was a fixed length, meticulously defined and physically embodied in master rods made of stone or bronze. These official standards were kept in temples, the sacred and administrative centers of the city, and copies were distributed across the empire. A builder in a remote town could compare his own measuring rod against the certified standard to ensure his work matched the specifications for a palace wall or a bridge. For commerce, they established standardized weights like the shekel and the mina. A merchant would carry a set of stone weights, each one carefully shaped and certified, to weigh out silver or barley on a balanced scale. This removed the ambiguity from every transaction. A mina of wool in the city of Ur was the exact same as a mina of wool in Babylon itself. This consistency was the bedrock of trust in a vast trading network. The genius of their system extended to its mathematical heart, the base 60 framework. This sexagesimal system was remarkably versatile, as 60 can be evenly divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made calculations for dividing land, calculating volumes of grain, or apportioning materials for construction incredibly straightforward. The legacy of this choice is still with us every single day. Look at your clock, 60 seconds in a minute, 60 minutes in an hour. Look at a circle, 360 degrees, a number perfectly divisible in so many ways. This was not a coincidence but a direct inheritance from Babylonian metrology. Standardization was their hidden tool for scale. It meant that thousands of laborers spread across dozens of construction sites could all work from the same set of instructions. It meant that the empire's wealth could be accurately counted, taxed, and redistributed. By giving the ancient world a common ruler and a common scale, they built an invisible framework of efficiency and fairness that allowed their grandest ambitions to become a unified, measurable reality. Their success in measuring the land and the day demanded a mastery of the year itself. Babylonian astronomers turned their gaze upward, charting the silent, predictable dance of the moon and stars. They did this not for abstract wonder, but to solve the most pressing problem of any agricultural society, knowing precisely when to plant and when to reap. Their lunar calendar was a triumph of long-term observation, a complex system designed to synchronize human activity with the cosmos. They tracked the cycles of the moon with meticulous care, marking the first sliver of a new crescent as the start of each month. But a year of 12 lunar months is about 11 days shorter than a solar year, the true cycle of the seasons. If left uncorrected, their calendar would quickly drift, and a spring planting festival would soon occur in the dead of winter. To fix this, their astronomer priests inserted an extra month, a leap month, into their calendar at carefully calculated intervals. This kept their agricultural and religious years perfectly aligned with the turning of the seasons. The result was a powerful, predictive tool. A farmer did not have to guess when the spring floods might come. He knew because the calendar and the stars told him that the time to prepare the fields was approaching. He could sow his barley with confidence, trusting that the rains and warmth would follow as predicted. This precise timing was a hidden force multiplier for their agriculture. Planting even a week too early or too late could mean the difference between a bumper harvest and a failed one. By embedding this celestial knowledge into the very rhythm of their society, they eliminated that uncertainty. This cosmic schedule governed everything. It dictated the dates for religious festivals that honored the gods of fertility and harvest. It set the administrative year for tax collection and the renewal of official duties. The stars became a silent partner in their survival. Their movements translated into a practical guide for feeding a civilization. This was the ultimate fusion of science and daily life, a hidden innovation where the vast, impersonal clockwork of the heavens was harnessed to ensure that every single field and every single meal arrived exactly on time. That silent partner in the sky guided the seasons, but another innovation harnessed an invisible force here on Earth to propel their world forward. The Babylonians took the ancient concept of the sail and refined it into a powerful engine of commerce for their river highways. Their boats, once dependent on the relentless labor of oarsmen or the slow drift of the current, could now catch the wind itself. This was not a simple cloth hung on a pole. It was an optimized system, a careful balance of material and design perfected for the unique challenges of the Tigris and Euphrates. They crafted their sails from tightly woven fabrics, creating broad, durable surfaces designed to capture the prevailing winds that swept across the Mesopotamian plain. The rigging was a network of ropes and pulleys, allowing sailors to adjust the angle and shape of the sail, to tack against the wind or run freely with it. This mastery of wind power transformed the economics of travel. A boat laden with heavy goods like grain or timber could now make a journey in a fraction of the time with a fraction of the crew. The human energy once spent on rowing could be redirected to loading, navigating, and protecting the cargo. Think of the sheer volume of trade this unlocked. A merchant in Babylon could now reliably ship vast quantities of barley north to Assyria, or receive shipments of precious metals and stone from distant mountains, all carried on the wind. This expanded network did more than just move goods. It wove the cities of Mesopotamia into a single, integrated economy. Ideas, technologies, and cultural practices traveled just as freely as the cargo carried along these newly efficient river routes. The sail was a quiet revolution in connectivity, a hidden advancement that turned their great rivers from simple boundaries into dynamic, flowing streets, binding their world together with threads of woven cloth and the boundless energy of the air. Their mastery of water and structure found its most beautiful expression not in canals or walls, but in the creation of living art. The legendary hanging gardens of Babylon stand as a testament to their ambition to weave nature itself into the urban fabric. While their exact form is lost to time, the accounts describe a breathtaking marvel, a multi-leveled garden of terraced greenery, a man-made mountain of fragrant trees and colorful flowers rising against the dry Mesopotamian sky. This was no simple patch of grass. It was a monumental feat of environmental engineering, a deliberate and stunning manipulation of a harsh climate into a cool, lush oasis. The central challenge was irrigation, and their solution was a symphony of hydraulic ingenuity. To lift life-giving water to the highest terraces, engineers likely employed devices like the shaduf, a long pivoting beam with a bucket on one end and a counterweight on the other, allowing a single laborer to lift water from a canal and swing it to a higher basin. For even greater heights, they might have used an Archimedes screw, a spiral pump within a cylinder that, when turned, could continuously draw water upward. A network of these devices working in stages could have channeled water to the very pinnacle of the gardens, where it would then cascade down from terrace to terrace, nourishing each level in turn. The gardens were more than a royal vanity. They were a public statement of control and creation, offering a shaded, fragrant retreat from the dust and heat of the city. The rustle of leaves and the sound of trickling water would have provided a sensory haven, a deliberate escape crafted by human hands. This concept of the engineered garden, a green space consciously designed for beauty and respite within an urban setting, is a profound Babylonian legacy. It reveals a society that understood a fundamental human need, the need to be surrounded by growing things, and possessed the technical brilliance to fulfill that need against all odds. The echo of this idea can be found in every city park and public square today, a hidden innovation that reminds us a city is not just a place to live, but a place to truly breathe. That intricate dance of shadufs and screws in the gardens, the precise angles of a ziggurat, all of this complex engineering would have been lost without a system to capture it in time. The true backbone of their entire civilization was not a machine of wood or stone, but the very act of writing itself. Cuneiform script, with its distinctive wedge-shaped marks pressed into wet clay, became the silent engine of their progress. This was no mere language for poetry or kings. It was the world's first technical documentation system. Scribes, trained in specialized schools, meticulously recorded every critical detail of their engineering endeavors. A single tablet could hold the exact dimensions for a new irrigation canal, specifying its width, depth, and the crucial slope needed to maintain a steady flow of water. Another might contain the mathematical calculations for the number of bricks required to build a city wall, or even a form of blueprint for a temple's foundation, showing the layout of rooms and the placement of load-bearing walls. These tablets were not stored away as historical curiosities. They were active, living reference manuals. An engineer in one city could send his plans to a colleague 100 miles away, and the instructions would be perfectly understood. A master builder could pass his hard-won knowledge about structural stresses or waterproofing mixtures directly to his apprentices, preserving lessons that would have otherwise taken a lifetime to learn. This created a powerful continuity. A canal maintenance technique perfected during one king's reign would not be forgotten after his death. The best practices for forging bronze or constructing an arch were captured, refined, and built upon by each successive generation. This cumulative knowledge, etched in durable clay, was the hidden force that allowed their engineering to evolve from simple solutions to true masterpieces. Every time they pressed a stylus into clay, they were not just writing words, they were building a permanent library of innovation, a shared mind for their civilization that turned individual brilliance into a lasting legacy for the world. Those scribbled tablets detailing construction plans held another secret, one of pure physical force. Babylonian engineers unlocked a fundamental truth that a small force applied intelligently could overcome a massive weight. They mastered the lever, a simple bar pivoting on a fulcrum. By placing the pivot point close to the heavy object, a team of workers pushing on the long end of the lever could generate enough force to pry up a stone block that would otherwise be completely immovable. It was a silent multiplication of human strength. For lifting those stones to the soaring heights of a ziggurat, they employed an even more elegant device, the pulley. A rope threaded over a grooved wheel mounted on a wooden frame changed the direction of the pull. Instead of trying to lift a heavy brick vertically, straight up, workers could now stand on the ground and pull down on the rope, using their own body weight to assist them. This was far safer and more efficient than a precarious human chain scrambling up a ramp. But their true genius emerged when they combined multiple pulleys into a system. A single pulley only changes direction, but when you add a second, third, or fourth pulley to the arrangement, something remarkable happens. The force required to lift the weight is divided among the number of ropes supporting the load. With a 4-pulley system, a single laborer could theoretically lift a weight 4 times heavier than he could manage alone. Imagine the scene at the base of a rising temple wall. A team of oxen or a group of men pulls on a rope that snakes through a wooden frame of several pulleys. Slowly, with a steady, controlled motion, a massive carved stone ascends, swinging gently into the air before being guided into its precise place high on the wall. This was the hidden machinery behind their grandeur. These simple machines did not just make work easier, they made the impossible possible. They allowed the Babylonians to accelerate their construction timelines dramatically and to build on a scale that would have otherwise consumed unimaginable amounts of human life and time. The lever and the pulley were their silent partners in lifting an entire civilization skyward, a profound understanding of physics that we still rely on every time we hoist a crate or raise a beam. The same engineering brilliance that raised ziggurats to the sky was channeled into a more terrestrial, urgent purpose, keeping enemies out. Babylonian defensive walls were far more than simple barriers. They were complex, multi-layered systems designed to make any assault a costly and nearly impossible endeavor. The legendary walls of Babylon, described by ancient historians with awe, were a masterpiece of this defensive art. Imagine a fortification so immense that its width could accommodate 2 chariots passing each other on its summit. This was not just a wall, it was a raised highway for rapid troop movement, allowing defenders to rush to any threatened point along the perimeter. But the walls themselves were only the beginning. Strategically placed towers projected outward at regular intervals. These towers created a deadly geometry for any attacker. Soldiers on the towers could fire arrows or drop stones on enemies attempting to scale the main wall, hitting them from the side in a devastating crossfire. This design eliminated blind spots and turned the approach to the wall into a killing zone. The gates were another feat of engineering psychology. Structures like the magnificent Ishtar Gate were not merely entrances, they were intimidating, heavily fortified choke points. A direct assault on a gate would force an enemy army into a narrow, confined space where they would be exposed to projectiles from above and from the flanking towers. Often, these gatehouses were designed with multiple offset doors, forcing invaders to make sharp turns while under constant attack, breaking their formation and their momentum. Beyond the walls, engineers often incorporated moats, filling them with water from the nearby rivers to create yet another formidable obstacle. The construction of these defenses was a colossal undertaking that mirrored the building of their greatest monuments. It required the same meticulous planning for material strength, the same understanding of angles and stress distribution, and the same logistical genius to manage thousands of laborers. These fortifications were a clear statement of power, a visible declaration that the city within was wealthy, organized, and impregnable. The principles they established, the use of towers for flanking fire, the strategic design of gatehouses, and the layered defense of walls and moats became the foundational textbook for military architects for centuries. From the castles of medieval Europe to the fortified cities of the ancient world, the hidden logic of Babylonian walls echoed through time, a permanent lesson in the art of protection. Perfection in construction required a tool that could literally point the way. The Plumb Bob was an answer of beautiful simplicity, a weighted object suspended from a single string. When held against a newly built wall, this device revealed an undeniable truth, the unerring line of gravity. If the wall was true, the string would run parallel to its face. If the wall leaned, even by the width of a finger, the string would betray that flaw, hanging at a clear and visible angle. This was the ultimate arbiter of vertical integrity. For the builders of a ziggurat, where each tier had to be perfectly centered over the one below, the Plumb Bob was non-negotiable. A single leaning wall could create a cascade of structural stress, threatening the entire monument. The same principle applied to the construction of their formidable defensive towers. A tower that was not perfectly plumb would be weaker, more susceptible to the relentless push of siege engines or even its own immense weight over time. This humble tool was a direct physical manifestation of the standards set by Hammurabi's code. A builder checking his work with a Plumb Bob was not just ensuring his craft, he was verifying his own survival and that of his family. It enforced a discipline of precision that became second nature, ensuring that every wall in every city met the same unwavering standard of quality. The legacy of this tool is its profound invisibility. You do not see the Plumb Bob in the finished structure, but you experience its result in the enduring stability of walls that have stood for millennia. It is a testament to their understanding that true strength is not just about mass, but about perfect alignment with the fundamental forces of the world. The same grains that fed the empire also fueled its spirit. The Babylonians transformed their agricultural bounty into something more than mere sustenance. They engineered beer brewing into a systematic, large-scale industry. This was not a haphazard kitchen craft, but a carefully controlled process conducted in specialized facilities that functioned like ancient factories. Their brewers worked from standardized recipes, meticulously recorded on clay tablets, which specified precise quantities of barley, emmer wheat, and dates, along with a mysterious ingredient known as bapia, a kind of beer bread that helped with fermentation. These recipes were repeatable formulas, ensuring a consistent product batch after batch. The scale of production demanded its own engineering. Vast fermentation vats, often made from bitumen-sealed pottery or even carved stone, held the bubbling mixtures. Specialized ovens baked the bapia, and an entire logistics network of canals and carts was needed to distribute the finished product to taverns and ration stations across the cities. They did not produce just one type of beer. Their brewers created a spectrum of brews, from dark, thick, and nutrient-rich beers for the laboring classes to lighter, finer, and more expensive brews for the elite and for temple offerings. This stratification was a masterstroke of economic engineering. Beer became a fundamental unit of the economy. Workers on massive construction projects, like the ziggurat or the city walls, were often paid their daily wages in beer, along with bread and onions. A standard worker might receive 2 liters of beer per day, a ration that provided crucial calories, hydration, and nutrition. Think of the social stability this created. A worker knew his labor had a direct, tangible reward, a comforting and familiar staple delivered reliably each day. This system turned beer from a simple beverage into a form of currency and a tool for social control, preventing unrest and ensuring a motivated workforce. The techniques they perfected did not remain within their borders. Through trade and cultural exchange, their knowledge of large-scale brewing traveled to Egypt and across the ancient world, seeding a tradition that would span millennia. The hidden innovation was not the drink itself, but the industrial system behind it, a brilliant application of engineering principles to the culinary arts that quenched a city's thirst and cemented its social order. Those same stars that guided the calendar also charted a course across the land. For a merchant leading a caravan of precious goods through the featureless desert night, the sky was not a spectacle, it was a map. The Babylonians transformed their profound astronomical knowledge into a practical tool for navigation, creating detailed star charts that served as the ancient world's global positioning system. They meticulously identified and named constellations, tracking their predictable journeys across the heavens. A merchant would know that when a certain cluster of stars, perhaps our Ursa Major, hung in a specific position, it marked a direct path north. The steady glow of the planet Venus could indicate a westerly direction at dusk. This celestial literacy turned the vast, intimidating darkness into a familiar and reliable guide. It meant a caravan could travel during the cooler night hours, avoiding the brutal heat of the day while staying confidently on course. This was a monumental reduction of risk. A journey that might have been a gamble, prone to getting lost and running out of water, became a calculated, predictable enterprise. The stars told them not only where to go, but also when to go. Their understanding of the seasons, derived from those same astronomical observations, informed merchants of the best times to embark on long journeys, avoiding seasonal floods in river valleys or sandstorms in the deserts. This hidden application of science directly fueled their economic engine. By making trade routes safer and more reliable, they ensured that lapis lazuli from Afghanistan, cedar wood from Lebanon, and copper from Anatolia could flow steadily into the heart of Mesopotamia. The exchange was not just in goods, but in ideas, technologies, and culture, all moving along pathways lit by the silent, steady light of the stars. This fusion of cosmic science and earthly commerce reveals a civilization that saw no boundary between the heavens above and the progress they could achieve here below. This same ingenuity that brought clean water in also had to devise a way to carry filth and rain out. Within the heart of their bustling, densely populated cities, Babylonian engineers confronted a silent threat: the constant accumulation of waste and stormwater. Left to fester, this runoff would have turned their straight, beautiful avenues into muddy, disease-ridden swamps. Their solution was a hidden network beneath the streets, a system of drainage and sewage that became a quiet guardian of public health. They engineered the very ground they walked on, creating graded surfaces that sloped gently toward carefully placed gutters and channels. These channels, often lined with fired clay bricks sealed with bitumen, acted as arteries for runoff, channeling rainwater away from buildings and public squares during a sudden downpour. For more direct waste removal, they employed clay pipes, ingeniously designed to fit together, creating continuous conduits that carried waterborne waste from residences and administrative buildings out toward the river or into designated seepage pits. This was a profound understanding of urban hygiene. By systematically removing stagnant water and waste, they drastically reduced the breeding grounds for mosquitoes and other pests, and they minimized the contamination of the public water supply. Think of the alternative, a great city like Babylon with thousands of inhabitants without any plan for sanitation. The stench would have been unbearable, and waterborne diseases like dysentery and typhoid would have been a constant, deadly presence. This infrastructure was a silent, unseen declaration that a city's greatness was measured not only by its temples and walls, but by the health of its people. It was an early, brilliant form of environmental engineering, a hidden innovation that flowed beneath the feet of every citizen, ensuring that the grandeur above ground was matched by a commitment to well-being below. Behind every transaction in the bustling marketplace and every calculation for a new canal, there was a hidden tool of pure speed. The Babylonians engineered a device to master the very numbers that ran their world, an early form of the abacus. In a society built on trade and complex administration, the need for rapid, accurate arithmetic was constant. A merchant needed to calculate the value of a shipment of barley in silver shekels. A tax collector had to sum the annual contributions from dozens of villages. An engineer had to compute the volume of earth to be moved for a new reservoir. Doing this with only a stylus and clay tablet was slow and prone to error. The abacus changed everything. It was a physical representation of their base 60 number system, with different rows or columns representing different place values. A user could slide beads or tokens along grooves in a board, each movement instantly adding or subtracting a value. This tactile method transformed abstract calculations into a swift, visual, and kinesthetic process. A complex multiplication that might have taken a scribe several minutes could be completed in mere moments. This was more than just a convenience. It was a force multiplier for their entire economy. In the noisy market, a trader could finalize a deal on the spot, his abacus providing an undeniable tally. In a government warehouse, clerks could inventory incoming goods with a new level of efficiency, reducing the opportunities for fraud or simple mistakes. On a construction site, a foreman could quickly recalculate the number of bricks needed after a change in the design, keeping the project moving without costly delays. The abacus did not replace the scribe, but it empowered him, freeing his mind from the drudgery of basic arithmetic to focus on more complex problems. This hidden innovation in data processing, this ancient calculator, ensured that the wheels of commerce and state turned more smoothly and reliably. It was the final, crucial piece in their engineered world, a system that managed not just water and brick, but the invisible, essential flow of information itself. These 28 innovations are not just footnotes in a history book. They are the silent pillars of our modern world, a legacy etched into the very framework of our daily lives. Every time you glance at a clock, you are reading the base 60 mathematics of a Babylonian scribe. The 60 minutes in your hour and the 360 degrees in a circle, are direct inheritances from their versatile counting system, chosen for its beautiful divisibility. When you drive through a city laid out in a grid, you are navigating a plan perfected in the streets of ancient Babylon, designed for order and efficiency. The arch that supports the bridge you cross, the concept of zero that powers the computer you use, even the standardized bricks that build the home you live in, all trace a line back to the fertile plains between the Tigris and Euphrates. Their engineering was not about mystery or magic, but about a profound and practical ingenuity. It was the application of keen observation and relentless problem-solving to the challenges of survival and growth. They looked at a landscape of mud and flood and saw the potential for ziggurats and aqueducts. They turned the unpredictable stars into a reliable calendar and the invisible force of gravity into a tool for plumb bobs and irrigation. This legacy offers us a powerful lesson in sustainability. They were masters of working with their environment, not just conquering it. They used local materials like clay and bitumen to their ultimate potential, and they designed systems from their canal networks to their legal codes for long-term stability and resilience. Their world was built to last, and in many ways it has. By studying their achievements, we connect with a deep heritage of human creativity. It reminds us that progress is rarely a sudden leap, but a cumulative process, a conversation across centuries where we are still building upon the forgotten breakthroughs of a civilization that first dared to engineer the impossible. Our journey through 28 hidden innovations reveals a civilization whose genius was not in magic, but in method. These Babylonian engineers looked at mud and saw the potential for soaring arches. They watched the stars and created a calendar for planting. They faced the chaos of flood and drought and responded with a web of canals that birthed an empire. Every solution, from the brick in the wall to the zero in a calculation, was a deliberate step toward taming their world and building a legacy meant to endure. This legacy is not confined to museums. It lives in the grid of your city streets, in the 60 minutes of your hour, and in the strong, silent arch over a doorway you pass through every day. These are the quiet echoes of a civilization that first dared to engineer the impossible. If this exploration into the roots of our modern world has sparked your curiosity, we would love to hear which innovation surprised you most. Share your thoughts below and subscribe for more journeys into the mysteries of our past. Thank you for uncovering the secrets of Babylonian genius. May their story of relentless problem-solving inspire your own quest to build, to learn, and to see the hidden wonders in the world.